All right, so here's a little bonus video. We're going to be talking a little bit about p-values and how we can apply this back to the literature. So when you're evaluating like a typical research question, it's most easily expressed in terms of there being some sort of difference between groups. So in this case, we're going to be looking at patients with acute myocardial infarction and whether or not the administration of IV nitrate, so this would be IV nitroglycerin, reduces mortality. Okay, so we'll cover this more when we get to the cardiology section, but this is a question that people had for a good long time. And so the most appropriate type of study design for this would be what we call a randomized controlled trial. Essentially randomized meaning that you had patients coming in with acute MI, you would randomize them to either receiving IV nitroglycerin or they would have a control group, which is why you get that controlled trial, where they would be receiving nothing, right? Or they would receive some sort of blinded type of drug where you would see, some patients would receive saline probably to mimic the infusion of IV nitrate, even though they're not receiving any drug. But anyways, that's a randomized controlled trial essentially. You have a control group and you have your experimental group who is getting the IV nitrates. So then the challenge now is to interpret the results of the study to see whether or not IV nitrates have any effect on reducing mortality. So any observed difference between these two groups could be due to the treatment, or it could be simply due to random chance, right? So in this case, our null hypothesis, which we always need to define first, would be expressed as the administration of IV nitrate has no effect on mortality in patients with acute myocardial infarction. Okay, and so based on the results of this, if we did find a difference or not, the idea would be you could extrapolate this back to all patients with acute MI and seeing whether or not we should, on a routine basis, administer IV nitrates or not. Okay. Hypothesis testing is going to help us to explore how likely it is that the observed difference that we see is going to be seen by chance alone, or and that would be the case if the null hypothesis is true, or if we can reject the null hypothesis and say that it's very unlikely to be due to chance alone, and there is a true difference in mortality between patients who receive IV nitrates versus not. So we have 6 trials that we see here that were performed looking at, you may have a little bit different inclusion or exclusion criteria, but basically what we're going to find is that you'll see, my laser pointer, basically we have different trials. These are usually the lead authors are going to be referring to, and we're going to have IV nitrate groups. We're going to see the number of patients who died versus the total number that were randomized. So you can see here in this Cheech trial, 3 patients died versus a total of 50 that received IV nitrate. And with the control group, 8 patients died versus 45 or the control group in total. And so what you'll notice here is that in general, the groups should be roughly equal. You should have roughly the same number of patients in the treatment group versus the control group. You can see here, this is pretty much kept in line. 154 in this drug debt. I don't know if that's really the right way to pronounce it, but 154 patients in the treatment group versus 156 in the control group. So again, things should be pretty even here. And so what we're going to be looking at is we're comparing the odds of death in the IV nitrate group to the control group. So we do the odds, typically what you see is say 3 divided by 50, and you divide that by 8 divided by 45. So we see the odds ratio of 0.33, and then you would see that they would generate a confidence interval to go along with this. So in this case, the confidence interval ranged for odds ratio of 0.09 up to 1.13. Now, one of the things you'll notice here is that because we are looking at ratios, our level of significance. So again, if there was no difference between the groups, if you were to divide the odds of those that died in the treatment group versus the control group, the odds ratio should be 1. Right, basically meaning that the odds of dying in one group versus the other are completely the same, and that ratio should be 1. Because again, if it was 10% in one group, 10% in the other group, 10% divided by 10% is still 1. So in this case, we see an odds ratio of 0.33. So it appears to be a much lower odds ratio of dying if you were in the treatment group than if you were in the control group. But looking at the confidence interval, we're going to see that it does contain 1, right? And for these odds ratios, when we're dealing with ratios, 1 will be our level of significance here. So if it crosses 1, then you know it's not going to be significant. So this range between 0.09 to 1.13, so very wide confidence intervals. Again, notice it's going to be around the odds ratio. So again, it goes below 0.33, it goes above it as well. And it's not going to be necessarily symmetrical. But you can see here that this is backed up by our p-value is 0.08. We said that typically p-value is less than 0.05 is going to be considered significant. Right? It's our alpha that we're setting. And so in this case, it crosses 1, and this makes sense because the p-value is greater than 0.05. Okay. Alternatively, if you were to look at, say, the odds ratio, so again, the odds here of dying in the intravenous nitrate group in this Busman trial was 4 out of 31, compared to the control group of 12 to 29. Here you see you have a smaller odds ratio, so the odds of you dying after getting nitrates is lower than if you were to have no IV nitrates in this trial. Here you can see that the odds ratio, or the 95% confidence interval, ranges between 0.08 up to 0.74. So this is going to be considerably more narrow than what we would see with the previous trial above. And here, because this does not cross 1, you can look to see the p-value is less than 0.01. Does that make sense? So again, in a lot of these cases, if you know if you're dealing with an odds ratio versus something like relative risk, you don't even need to see what the actual p-value is. You can just look at the 95% confidence intervals and know whether or not the results are significant. Okay. I won't go through each one of these, but just be aware that you can kind of look back at this to see whether or not these results are going to be significant or not, and compare those. We'll go into more detail on these individually in just a second. So the results from the 6 trials of IV nitrates are given on that table we saw, and again, this is pretty old data. This is back from '88. So again, we've kind of come a long way from here, but again, this is good for historical reference. So in the first trial, in the Cheech trial, 50 patients got randomly assigned to receive IV nitrate versus 45 were randomly assigned to the control group. At the end of the follow-up, 3 of the 50 patients given IV nitrate had died versus 8 in the control group. The interpretation there of the confidence intervals indicates that the true odds ratio in the population from which the trial subjects were drawn, so again, all the population of people with acute MI, would likely be between 0.09 and 1.13, right? So for somewhere between there, we either have a reduction in the odds of death by getting IV nitrates or an increase in the risk in the odds of death. Okay, so again, it's not usually what you want to see in these kind of cases, but again, we have that range there. And again, because it crosses 1, we see that the p-value is not going to be significant. Now, if you initially ignore the confidence intervals, you're going to see that 5 of the 6 trials summarized in the table have odds ratios that are consistent with the protective effect, meaning that the odds ratio is less than 1. And again, when you're calculating this odds ratio, all you do is you're taking that, for in this case in the Busman trial, you do 4 divided by 31, which is the odds of dying in the nitrate group. You take 12 divided by 29, which is the control group, and you just divide one by the other, and that gives you a ratio of 0.24. And you can do that math yourself. It's pretty straightforward. So what you see is these range from a risk reduction of 17% in the Flaherty trial to one of 76% in the Busman trial. This means, in other words, that in the Busman trial, the risk of dying in the nitrate group is actually about 1/4 of that in the control group. And so you can see pretty wide-ranging odds here. In the remaining trial, in the Jaffe trial, you can see that the odds ratio was 2.04. So this would actually this would predict that the IV nitrate would actually be harmful. This could actually double your odds of dying in those if you were to receive IV nitrates. So when looking at the p-values in the final column of the table, this is going to give us an indication of just how likely it is that those differences are going to be due to chance alone, right? Anything greater than 0.05, the likelihood that these results are just due to chance are too high, and we cannot reject our null hypothesis. When you're looking at the Cheech trial for the first one, this is going to indicate the probability of observing an odds ratio of 0.33 or more extreme than that, so something lower than that, if the null hypothesis is true, is 8%. Right, or 0.08. So because of that, this means that the risk is, or the chances of this being due to random variation is too high, and we cannot reject that null hypothesis in those cases, right? This basically, you would see that, equivalently 2 out of 25 would show just such a chance effect. It's unlikely that our management of these critically ill patients would be altered based on this evidence alone. It's not statistically significant. Clinically, it would not really help us out a whole lot to decide how we should treat our patients. Okay, and again, if you would take these results by themselves, you would probably say IV nitrates are no good. We shouldn't really be using these for acute MI patients. Okay. So this is why we do multiple trials. We want to look at this in several different instances to see are they all consistent? Do they all show no significant difference, or are some of them going to be more likely to show, especially if you have larger sample sizes? So if we look at the Busman trial, similarly, this would indicate that 1 in 100 trials would have an odds ratio of 0.24 or more extreme just by chance alone. So again, this would be a significant p-value here because it's less than 0.05. And again, that 95% confidence interval does not include 1, so we could just predict from this that the p-value is going to be less than 0.05. So in this case, we would see a protective effect of giving IV nitrates because the odds were about 1/4. If you were odds of death are about 1/4 of what you would see in the IV nitrate group versus the control group. So comparing p-values across all those trials are going to offer two main features of interest. One, the first is that the size of the p-value is related to some extent to the size of the trial. And again, the larger your sample size, the more likely you are to see smaller p-values, right? Because this means you have more statistical power. You guys remember that from the last lecture. So again, looking at the drug trial, we see 154 patients in each group, roughly, versus just 64 and 76 in this list trial. We can see the p-values end up getting a lot smaller. So again, more people in your trial, more power to see a true difference if one actually exists there. Okay, it means you're less likely to make a type 2 error. So this is what we see in general as what you'll see in larger trials as you observe those. What we can also see is that the p-value is going to change with the size of the observed effect. So if we were looking at Cheech and Flaherty trials, they have kind of broadly similar numbers of patients, but you're going to see that the smaller p-value occurs in the Cheech trial. So we're looking at Cheech versus Flaherty. You can see here that the sample sizes are roughly the same, but you're going to see here the odds ratio is much, much lower than what you saw here with the Flaherty trial, right? And so because of that, because we have a larger effect size, we have a larger reduction in those odds, you're going to see that the p-value is much smaller. So again, to find a value that extreme, it is going to be less likely just due to random chance. So you can see that, in this case, it's 0.08% that this random variation would show a result as extreme as this or more. But in this case, because you have such a small reduction in odds here, or small odds ratio, you would see that the p-value here is actually pretty large. So again, this would be 70% of the time you can find a result as extreme or more extreme than that if you were to keep running those trials over and over again. Okay, so again, the more extreme the effects you're going to see, the smaller the p-value in general. So when considering those confidence intervals shown on the table, again, for odds ratios of the Cheech study is 0.33. This again would suggest that the IV nitrate reduced that mortality by about 2/3, which looks pretty good. But the confidence interval would indicate that the true effect could be anywhere between a 91% reduction up to an increase in 13% based on this 0.09 to 1.13. So again, you can either find a very substantial reduction in mortality, or you may actually find that IV nitrates are dangerous. We just can't tell from this because we cannot reject the null hypothesis because that p-value is greater than 0.05. Because this includes our odds ratio of 1, which is the null hypothesis, we cannot reject anything here. So again, the confidence interval for the Busman study was 0.08 and 0.74 is going to provide a more kind of positive picture here. Again, this does not cross 1, so we know this is going to be a statistically significant result. So this means that it could indicate a reduction in mortality as little as 26%, as you can see here, 0.74, to as much as 92%. So again, in this case, you would find little evidence to suggest that the IV nitrate may be harmful, and therefore it would be more reasonable just based on the results of this study that would be more likely to be beneficial for your patients. Okay. In this case, because the p-value is 0.01, there's a 1% chance that a result as extreme as this or more extreme is due to just random chance alone. Again, most of the time you're going to find that one positive trial result is not enough to change clinical practice unless it is a very, very large trial dealing with thousands and thousands of patients. It's very unlikely that a result such as this is going to make everyone start to use IV nitrates for patients versus not. So again, the overview of those trials was carried out because the results did not really appear to be consistent. And in general, those trials were too small to really provide reliable estimates of their effects. So what they did was they did a pooled analysis of all the data. They pulled all the data together to try to see if there's one kind of overarching effect that they can compare with one another to see if they can finally answer the question, is this application of IV nitrates going to reduce mortality or not? And so I'll show you the graph of what that looks like in just a second, but the odds ratios and the 95% confidence interval for each individual trial are going to be shown in the next figure. The odds ratio for each trial is represented by a box. The size of the box is going to be kind of proportional to the amount of statistical information available, and that's going to be shown in the 95% confidence interval is indicated by a horizontal line. Okay. The solid vertical line is going to indicate an odds ratio of 1, and this is going to be the line of no effect. I'll show you what that looks like in a second. And then looking at this combined odds ratio of all 6 trials is indicated by the dashed vertical line, and its associated 95% confidence interval is going to be the diamond at the bottom. All right, so looking at this, we have each of our individual 6 trials. And looking at the number of patients is going to increase the size of the box here. As you can see, larger box, especially that drug trial, is going to be a larger number of patients that are in there. You see the confidence intervals associated with each of these. And one of the things you notice is that that last trial, that drug debt trial, has a larger number of patients. Notice how the confidence interval is a lot smaller than something that had a small number of patients. Now, one of the things you see here is that if and again, 1 is this line of no effect. So if the confidence interval crosses this line, this means that there was no statistical significant results found. Okay, so that means that really the only trials that showed statistical significance, and you can look back on the table to show that, would be the Bussman trial. It would be this drug debt trial. Everything else crossed that line. We cannot say that we can reject the null hypothesis. So then what they did by pooling all the data together, they found that, hey, this is the mean odds reduction, or odds ratio, that when you looked at all these patients put together, and then here's the 95% confidence interval. So this would appear that when you combine all this data together, notice here it does not cross 1, that giving IV nitrates appears to be beneficial to your patients with acute MI. Again, this is backed up by the numbers. The pooled analysis resulted in an estimated overall odds ratio of 0.53, so about a 47% reduction in the odds of death, with a confidence interval between 0.36 and 0.75. Notice it does not cross 1. This would be considered statistically significant. Okay. If you were to look at the confidence intervals from individual studies, it showed a high degree of overlap with the pooled confidence interval, which again you would expect, and that all the evidence appears to be consistent with the pooled estimate. Okay, so again, there's not really many studies that showed a harmful effect, even from the Jaffe study. But again, most of the data tend to be consistent, which is good to see. Again, the p-value for the pooled analysis was 0.0002, indicating that we had a big effect and we had a large sample size. So this would indicate that it's very, very unlikely that we would get a result like this again, just due to chance alone. So note, since that meta-analysis was reported, we've seen the treatment of acute MI has changed pretty dramatically since the introduction of thrombolysis. This is where we can actually go and use our clot busters. We can use things like TPA, and we have things like the cath labs. And so now we don't really rely on IV nitrates quite as much as we used to. And in fact, there was a large study called this Fourth International Study of Infarct Survival, or ISIS-4, and they randomized over 58,000 patients with suspected MI. And they actually found no evidence to suggest that mortality was reduced when you actually give an oral nitrate. So again, not quite apples to apples here, but again, we can find that our current understanding is that nitrates don't tend to be all that helpful in reducing mortality. But they are very good for helping symptom control and for blood pressure. We'll talk more about that in pharm when we get to the cardio section. So anyway, that concludes it for our p-value exercise. Hopefully this helps drive the point home a little bit more and make it a little bit more concrete in how we can apply p-values and confidence intervals in our understanding of the literature. Thanks, and send me any emails if you have questions.